Okay, so in this video what we're going to do is we're going to see the definition of continuity of a function between two topological spaces, and then what we're going to do is see how if you have a continuous function between two metric spaces, and then you view those metric spaces as topological spaces, because we know that if you have a metric space you can define a very nice topology on it, i.e. you can let the topology equal the set of all open sets, and that defines a perfectly good topology, and a very, very natural topology to define on the metric space as well. Very much so related to the metrical structure of that space. Okay, and what we want to make sure is that if the function is continuous in the metrical sense, then it's also going to be continuous in the topological sense, and moreover, if it's continuous in the topological sense, it's also going to be continuous in the metrical sense. That's what the aim of this video is to prove. But before we can do that, what we need to first do is define what is meant by a continuous function between topological spaces. So I'll just call that topological, topological definition of continuity. Now, the first thing to note is that in the metrical definition of continuity, there was this notion of continuity at a point, so point-wise continuity, and if you were continuous everywhere, that meant that you were just continuous at every single point. Now, in the topological definition of continuity, the definition is much more global. A function is continuous. It does not really, well, there may well be, I don't know, I can imagine that you can define a point-wise topological continuity, but the concept is only really useful when you have a global continuity, i.e. where it's continuous everywhere. So this is the definition of continuity of two maps between two topological spaces. So let's say we have a topological space X and curly U. So remember, this is a set with a set of subsets of the set, which is this curly U, and that obeys some axioms, i.e. it contains the empty and the whole set and the whole space. It's closed under finite intersections, and it's closed under arbitrary unions. And if you aren't familiar with topological spaces, see my video on metric and topological spaces. Or see some topology textbook or whatever. Here's another topological space, Y, and we'll say big curly U bar. Okay, and F is continuous if for all open sets over here, if U is an element of big U bar, so take any set which is in big curly U bar, so take any U which is an element of that big curly U bar, and basically if you take the inverse image of that, so F inverse of U, which is defined to be all points Y, which is an element of big X, such that F of little y is equal to is an element of U. So basically, this is a set. This U here is a set of points. So it's some open set, and I should have drawn it with a dashed line again. Drat. So any point in here. So this is a set of points, basically. And what I want you to define is this new set, which is F inverse of U, sometimes called the inverse image or sometimes called the pre-image, which is all points here. So let's say, we use the symbol little y for some bizarre reason. So all the points little y which are in this set, such that when you map them, when you map them into this other topological space, when you take F of little y, it's some point within there. So this is the pre-image or the inverse image of the set U. And basically, the definition of topological continuity says that this inverse image, this set over here, F inverse of U, must be an element of the topology on this domain, So this is the domain, and this is the codomain of the function. So basically, the inverse image of open sets must be open in the domain, basically. So this set here must be in this topology up here. Okay, so that's the definition of continuity. Open sets, the inverse image of open sets is open, is the way to summarize it in a line. Okay. So the main thing to note is that this is a global definition. It's not saying continuity at a point. It's saying continuity of the entire map. If I take an open set over here, its inverse image must be open. Okay, so now what we're going to do is we're going to try and understand why this definition coincides with the metrical definition in the case of maps between metric spaces. So here we have two metric spaces. So this is x with a metric d, and this is y with a metric d bar. And we have some function between them, f, which is continuous everywhere. So continuous on the whole metric space. Continuous on all of x, not just continuous at a single point. Continuous in the metrical sense everywhere. That means that if I take any little x here, then it has a point in here, f of x, and basically for all epsilon greater than 0, I can draw, and I'll rectify my mistake and draw a dotted line now. I can draw a ball, an open ball, around the point f of x of size epsilon, and basically for whatever size epsilon you make, I can find you an open ball around x, an open ball around x of size delta, such that there exists some delta such that this entire ball is mapped into there, and that works whatever point you are at, basically. That's the definition, that's the metrical definition of being continuous everywhere. Now, we know that metric spaces give rise to very natural topologies, and the way that you do it is you say, let the topological space be this set with the set U defined to be all open sets in the metrical sense of the word. All open sets, let's say metrical, where we defined open sets in the metrical sense to be all sets which are made up completely of points which are interior to those sets. So all sets that contain only interior points. An open set is a set where all the points are interior. Okay, and similarly we can define y and big curly U bar to be the topology made by this metric space over here. Okay, so if we want to prove that this function here is continuous in the topological sense, when we view it as a mapping between the two topological spaces rather than mapping between the two metrical spaces, we need to prove that if I take any open set over here, let's say U here, I need to prove that its inverse image is open over here. Okay, so how am I going to do that? Well, if I take, let's say, let's take the set U, which is an element of this big curly U bar, and I want to make, and this set is either this set is empty. U could be equal to the empty set, in which case the inverse image of U, f inverse of U, is going to also be the empty set, in which case it's open. Alternatively, U might not be the empty set, and then again there are two possibilities. F inverse of U could be empty. There could be absolutely no elements which are mapped onto it. I.e., if you think about it, if you this set could, the map might not be onto, basically. The map might not be surjective. If we think about the topological, the metric space being extended down here, and all of these points are just mapped into this bit up here, then all of the bits in here won't have any inverse image. So the inverse image will be empty. So, but if that's the case, that's fine, because phi is the empty set is always an element of the open set, so the inverse image in that case will be open. And then the other possibility is that f inverse of U is not empty. And then there's some element W, which is an element of f inverse of U. So let's say here is W in f inverse of U, and correspondingly over here there is f of W, which is the point it's mapped onto in the set U. Okay, so now what we want to prove is that this f inverse of U is open, And the way that we can do that, the way that we need to do that is to prove that any point in here is an interior point. So W is some arbitrary point in here. So we need to prove, required to prove, W is interior. So the definition of interior means that we need to find some epsilon neighborhood around W. We need to find, let's say, some delta. Well, actually, I'll say we need to find some. I need a little letter. Let's say eta. We need to find some eta, a Greek letter, some eta greater than 0, such that the ball around W of radius eta is completely contained within F inverse of U. That would mean that W was an interior point in F inverse of U, and that would mean that F inverse of U was going to be open. So that's what we need to do. Okay, so now the way that we do it is, just to recall, we have these two metric spaces here. We have an open set here, which is U. We have F inverse of U over here. F inverse of U with some W in here. And we have F, which is continuous. Okay, in the metrical sense. So this is a metric space XD, and we might say it's got that topology on it as well. And XD bar with the natural topology again. So it's got all this structure on it. But of course, the metric automatically gives these. So yes. Okay. Firstly, F of W is an element of U. F of W is an element of U. Since W is an element of F inverse of U. So if W is an element of the inverse image, then that, by definition, it's mapped onto a point in U. So F of W is the point it's mapped onto, so that is an element of U. Okay, but we know U, oh dear, what have I done curly U? Why is this curly U? This is U. U here is an element of this big curly U bar. So it's an element of this set of open sets. It is an open set in here. By definition, by assumption, we said we'd start with an open set, because remember, we need to prove that the inverse image of open sets is open. So we said start with an open set, U. Okay, that implies that F of W is interior. In U. Which implies there exists an epsilon greater than 0 such that the ball around F of W of size epsilon is completely contained within U. So basically there exists some open ball that I can take around that point, F of W, which is completely contained within the set U. Now we apply continuity. By metrical continuity, this implies that there exists a delta greater than 0 around such that the ball around W of size delta, basically if you take any little element y, which is an element of that ball, F of y must be an element of this ball centered around F of W of size epsilon. So basically I'm saying, okay, the function is continuous at this point W, because it's continuous everywhere on X by assumption. Therefore, I can find you a little open ball W around, a little open ball centered around W of size delta, such that this is completely mapped into that open ball of radius epsilon around F of W. Okay. Now this ball, if the image of this ball, which I'll write F of BWD delta, which just means the image of this ball, I'll write it out. It means the set F of little x, which is an element of y, such that x is an element of this open ball centered around W of radius d. So it means take all the points little x in this set, the open ball centered at W of radius delta, and take their image. That image is by definition, because the function is continuous, that is contained within the ball centered at F of W of radius epsilon. But this is contained within U, which implies that the image of f of this ball centered at W of delta is contained within U, i.e. all the points in this ball centered at W are mapped into the set U if they are mapped into this ball here. That's obvious from the picture. Okay, but then that implies that this ball of points centered at W of radius delta is completely contained within the inverse image of U, i.e. it's contained within this inverse image, just as I drew, which implies that W is interior, since this is our perfect ball we needed. W is interior in F inverse of U, because this ball here functions as this epsilon neighborhood we need. Simply set eta, what was the variable we were using, equal to delta, and we have our epsilon neighborhood, our eta neighborhood, if you like, our delta neighborhood, around this point W that's completely contained within the inverse image of U. That implies W is interior in F of U, and since W was arbitrary, it implies that F inverse of U is open, because all points must be interior, because this was just an arbitrary point, is open, which implies that the inverse image of open sets is open. So it implies that metrical continuity does imply topological continuity. Implies topological continuity. Oh dear. Topological continuity. Okay, so in the next part of this video, we will prove the other way around, that topological continuity implies metrical continuity.